Welcome to Evil Dojo, Project Euler number 12. Highly divisible triangular number. The sequence of triangle numbers is generated by adding the natural numbers. So the seventh triangle number would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 equals 28. The first 10 terms would be 1, 3, 6, 10, 15, 21, 28, 36, 45, 55. Let us list the factors of the first 7 triangle numbers. 1 is 1, 3 is 1 and 3, 6 is 1, 2, 3, and 6, 10 is 1, 2, 5, and 10, 15 is 1, 3, 5, and 15, 21 is 1, 3, 7, and 21, and 28 is 1, 2, 4, 7, 14, and 28. We can see that 28 is the first triangle number to have over 5 divisors. What is the value of the first triangle number to have over 500 divisors? Which one did I do first? 7. So So that should be the formula for triangle numbers. .28. Okay, that works. So we need a function to count the number of divisors in a number. So we're counting 1, right? Do we count the number itself? Yeah. So that'll be an optimization strategy. But let's just be naive about it to start with. For int I equals 1, I is less than n, I plus plus. If n mod I exactly equal to 0, count plus plus. And by the end, we should have the number of divisors that go into the number. If we wanted to be clever about this, we start from 2, and we could go to we could still go to n because it would never hit n. The count would start at 2 already because that would already include 1 and n. So it would always unless it was 1. then we just return 1. So the number of divisors for the triangle number of 7 would be 6. Now, here's the fun part. What is the value of the first triangle number to have over 500 divisors? Over 500, right? Let's see what that number is. Nuh-uh. Oh, my parentheses are way wrong here. Hold on. Choke my CPU for a moment. We're probably doing ourselves a disservice by starting at 1. Right? So maybe we could optimize this a bit. We're just going to print out a few. Let's print out triangle numbers from like the first 100. Why is it printing 2 things? Oh, at the very end, it prints out what I was. Oh, duh. Okay. So, the 99th triangle number has 36 divisors. Okay. So, mod is expensive, right? Like, is there such thing as like a fast mod? Because, I want to print out, alright, let's do 300. Like from 200 to 300, just for shits and giggles. The 299th has 48. So we're gonna have to go a lot higher. Let's try 1000 to 1100. So even then, it's gonna vary. Some have less than others. So it's almost like we're gonna just have to run through until like we get to like a new max divisor count. And honestly, after the last problem, everything should be unsigned long int. Just about. Okay, so now we're getting maxes, which is nice, because it gives me an idea of like how far up the chain we're gonna have to read. So every time we hit a new maximum, we got the index of where that number occurred. So like for instance, the 935th triangle number so like if we went to first 10,000, it was starting to choke a bit. Hmm. All the comparisons I'm doing here might be slowing it down a bit. Wouldn't think that much. But I guess computing each triangle number does take a long time. And really it's the modulus it's this loop. This process right here. It's taken us so long. Because it ends up being a doubly nested loop to get the divisors, right? One thing we could do is instead of going forward like this, we could actually try to pre-compute some of these, for instance. Divisor counts. I actually computed the triangle numbers really fast. It's the divisors that's slow. So, is there a fast way to compute divisors? let's think about this. If n is even, for instance, let's say it's 10, right? How do we get the number of divisors? So if we step through starting with 2, 2, 3, 4, 5, 6, 7, 8, 9, right? And actually, the largest number that we would have to check would only have to be half of the number itself. So we wouldn't even have to go that far. So for instance, for 15, the largest number that we would have to check would be 7.5. So right away, we can actually eliminate something like half of the values that we have to check for. Actually, the printout's slightly off, right? 1, 3, 6, 10, 15. Oh, let's see. 1, 2, 4, 4. 1, 2, 3, 4. What am I printing out? I'm printing out the new maxes. Oh, it's like which, 1, 2, 3. Less than or equal to. Okay, 1, 2, 4, 6. No, it should be 1, 2, 4, 4. Oh, those are the new maxes. Okay. So we should probably go ahead and list what the triangle number was, right? Okay, yeah. 28 is the 6th triangle number, or 7th rather. Minus 1. Oh yeah, that's better. All right, come on, let's get past that 320 hump. I mean, if the compiler's not fucking stupid, it would be half n equals n divided by 2. I is less than or equal to half n. So if it wasn't retarded, it would actually be storing the n divided by 2 and not recomputing it on every loop through. This is taking longer than I thought it would take. We need a fast modulus now. Let's go ahead and cut out the comparison. Right here. On the off chance that we just get lucky. Oh, wait. So for instance, if it's greater than 300, it breaks pretty early. The value of the first triangle number. So we would want to keep track of that as well. So the first triangle number to have over 300 digits, or 300 divisors, is the 2079th triangle number, and it's 2162160. For 350, we could also track how long this takes. And honestly, for the amount of time that we're waiting, we are interested in keeping track of this stuff. So for 300, it took 5 seconds. It's taken much longer for 500. But let's fucking go. I, T, and D. So, whatever the center number ends up being, it's got to be some optimization strategy that I'm missing here, though. This is fairly brute force. Choking up my CPU while I do this. Computing the triangle numbers, actually, we could do this recursively, but I thought I was trying to pre-compute stuff, and really, yeah, they're fast, so it's really the divisors that are slow. So, like, the number 4 in binary is 100. Right? And to divide that by 2, you can just shift bit by 1 to the right. So you end up with 10, which is 2. So if we wanted to take the number 3 and divide it by 2, shift right, 1, 1, you end up with 1, which is the remainder if you attempt to mod 3 by 2. Similarly, if we have 5, which is 101, and we mod that by 2, take 101, you shift right, you end up with 10, which is 2, which is the number of times that 2 can go into 5. We have no information about how many items remain, right? So let's think about this. Let's take 10, which is 1001, and we shift right by 1. We end up with 100, which is 4. No, sorry. 10 is 1010, and we shift right by 1. That leaves us with 101, which is 5. If we have 11, we shift right, which is 1011. You end up with 101, which is 5 also. We lose that information. But let's say you have 5 mod 3, right? So 5 divided by 3. So the divide by 2 is fast because we're literally only having to shift bits around. But 5 divided by 3 would be 1. So if we take 1 times 3 and subtract it from 5, we get 2, which is the remainder, right? So if we, instead of modding, we use simple division. And we do this, it might be faster than modulus for large numbers. We've already let the program run this long. It would feel like a cop-out to quit now. We know the code works. But it's so slow. It's taking forever. We could get to the end of 10,000 triangle numbers and never find one that has more than 500 as well. That's also a problem. We have no idea where in the process we currently are or how far in, but considering it finds the first item with more than 300 divisors pretty quickly, the next item, the item we're looking for must be very far away from that one. I'm actually going to let this run long enough to fucking either tire the loop out and cause me to get fucking mad, or it actually finds the number. But, oh fuck, we're also not going to know if it's the actual max T. Well, we will, because it'll be 0 if it didn't ever hit that if statement. Fuck, man. Oh my god, it didn't find anything. Oh my god, it ran for 5 minutes and it didn't find anything. Fuck. So you know what? We may not want to pre-compute on that front. So we still want to pre-compute, right? So if it's not in the first 10,000, fuck. See, I'm trying to avoid having to do this comparison on every iteration, right? So we could actually just So now, after Largest divisor counts. For the first 1,000, pretty fast. Is there any way to use recursion? Oh yeah, so here's something interesting. Um, 21 and 15 both have 3 as a divisor, right? And similarly, um, 7 is shared by 28 and 21. So if half of 21 is 10, and we attempted to mod in 10, we attempt to mod in 9, attempt mod in 8, and we mod in 7, right? So if we mod in 7, then that leaves us with 3. So I'm thinking if we take the initial n and then we start stepping down from half n, right? So in other words, if n is prime, but if it's a triangle number, it's not going to be prime, so I don't think so anyway. This is an example of how you might cut them out, right? So then, as we're stepping through, if n mod I exactly equal to 0, then n copy divide gets n. Count plus plus, right? So then we're going to want to return count. Oh no. Now here's another problem. What if we get through this whole thing and we never find anything? I don't think that would be true. Nor do I think we should need a loop like this. But it would avoid having to like test every single value and kind of reduce the amount of work that we have to do, I think. Yeah, that's not right. I still like the idea of going backwards, though. So we take 28 mod 2. That gives us 14. So it's almost like a reverse prime test, right? It's not half n, but square root of n. But here, we don't only go to square root of n, we only go to, or better yet, what is square root of 28? $5.29. So we test up to that point. Then So 28 mod 4 would be 7. 28 mod 2 would be 14. So the count would go up by 2. So in the first 1,000, the max number of dividers is 144. Oh, that was much faster. I don't know if that number's correct, but $100,000. Let's see. Is that it? Right there. This took me long enough. There we go. Oh, fuck. God damn, that took forever.